Okay. Hi, everybody. Today's lecture is about PLAIY Library, which is a LabVIEW library for machine learning. PLAIY Library was developed by TDS Group. TDS is the shortened name for the Technologies de France Group, which developed this library 2 years ago only for machine learning work in the environment of LabVIEW. So by using PLAIY, now we can use LabVIEW directly, and there is no need to work with the Python node. This is really an advantage. As I have found, PLAIY library is easier to work with if you compare it with the analytics and machine learning library of LabVIEW. And the PLAIY library is an open source library. This is another advantage. And it is really a serious advantage if you compare this with the analytics and machine learning toolkit of LabVIEW. Conversion here is exactly done for all the functions and classes and algorithms existing in SKLEARN and related to machine learning work. In this lecture, I shall show you the components of this library, and we shall carry out an example to illustrate for you how we work with this library. So at first, I want to show you the components of this library. I have opened a block diagram. I right-click on the block diagram, and here you will see the TDF, and against it you see the PLAIY, and against the PLAIY now you see other 4 or 5 different palettes, as they are called in LabVIEW. The first one is for datasets. So this library includes, as you see, 4 different datasets. One of them for toys, the other one load Boston housing data set, the other one load breast cancer data set, the next one load diabetes data set, load iris dataset, and load wine dataset. So as you see, this is a sufficient number of datasets which could be used directly and loaded from PLAIY. Really, this is analog to what we have found in SKLEARN. In SKLEARN, you remember also, we have there about 20 datasets, and there you will find also the breast cancer and the load diabetes and Boston and California dataset, and also the iris dataset. All of them exist in SKLEARN, and now they are existing in PLAIY. Really, we can work with them and we can work without them. We can download any dataset from any site or repository in the internet and convert it from CVS type file to a type file adequate for LabVIEW. This is easily done, and I shall show you that. So this is helpful in any way to work with these datasets directly for the beginners. But as I said before, you can use any dataset, whether it is downloaded from a site or you have created it as a synthetic dataset also. This is possible. Now, when we come back to the PLAIY, we shall see the other palette here, which includes data pre-processing VIs. Really, you will find a large number here, and it is much more than those existing in the analytics and machine learning toolkit. Here, they are more than enough. Very detailed choice of different processing algorithms you find here, as for example, feature extraction, or for example here, imputation of missing values, or here, random projection VIs, or as here, detailed kernel approximations, and fit transform VI, or data pre-processing in general, or transform only without fitting, decoding VI, partial fit VI, many other, because some of these palettes have sub-palettes, as you see here. For example, this is a sub-palette for example, binarize VI, or label binarize VI, or for example, polynomial features VI. All these VIs here are used for pre-processing activities when working with machine learning. Okay. Now, in addition to the data pre-processing, we have one important palette here, which includes a number of sub-palettes related to regression and related to classification and clustering also. If I put a cursor here, you will find a group which is supervised machine learning activities or algorithms. There you will find regression and classification. Here, for example, let me go back here. Yes, now this is PLAIY, this is, yeah, here it is supervised. Now, here is the classification subpalette and another subpalette derived from it, which includes the final VIs, which you will select in this aspect. For example, here, support vector machine classifiers, or here, discriminant analysis, or here, linear classifiers, here, if you want to use the matrix and to select, to find the score, to estimate the performance adequacy of the regression and classification processes. Here is fitting and so on. Also, we can go to unsupervised palette here, where we find a huge number, also a large number of sub-VIs, as you see here. For example, this is very famous one, DBSCAN-VI. Here is K-means VI, it is very known. Mean shift VI, optics VI, and others. Anyhow, let me tell you one thing here. All these VIs, you cannot remember them directly. You have to work on that personally and to try to know what each of them is doing. Let me show you how. I will go out from here, for example, and consider the example here, which I will illustrate for you just now. If you right-click, if you see here, you will find that this is a VI which represents linear regression. And if you click on the arrow here, you will find a large number of algorithms in addition to the linear regression. I have selected the linear regression, but you can, of course, select other, for example, like ridge or ridge cross validation or orthogonal matching pursuit and others. I have selected the linear regression because I am interested in it. Now, to learn about this VI, the most important thing is you right-click it. You right-click it here. I have right-click it. Go to the help, and now it will take you to the SKLEARN. Here now directly the linear regression. So at first you will see here the syntax of this algorithm, and now it will give you all the information and detailed information about this function and some examples, but these examples are in Python because this SKLEARN itself is a Python-based algorithm, but library. But the important thing here is to know about the function which you select from the PLAIY. So when we selected the linear regression, if you do not remember what it is or you need some details about it, you right-click there and you then will go to the SKLEARN to read about it. Here, for example, the initiate VI, it doesn't have a help. So you have to, here we don't have. The most important here is this VI because all the other VIs are really for pre-processing, but the predict VI here has a help. If you right-click it and press the help, it will take you also to the SKLEARN prediction and scoring and other relative informative topics which you can use. For example, as set parameters, here it is used in SKLEARN as a function here, but in PLAIY here, we shall set the parameters by using the property nodes. I shall show you that and talk about it a little bit later. So what I have done just now, I have told you that this PLAIY library is dedicated for machine learning only, and it is just a conversion of scikit-learn algorithms and functions to be used in LabVIEW environment. This library is very new, 2 years ago only. It is not yet published, but if you want to download it, you can go to the GitHub repository, and there you will find a terminal there, and you can download it directly. I downloaded it really through the VIPM of LabVIEW, VI package manager of LabVIEW. I used it and downloaded it into my computer. So shortly speaking, you can download it and you can go through all the elements in it, and you will have a good background to work with it. Before telling you and discussing about this program, I want at first to illustrate for you the same program but in Python, so that I shall get the results there and can compare the results which I get in Python with those which we will get by using PLAIY. So let us go first to Python so that I can illustrate for you, illustrate for you that example. Okay, I shall open my notebook, go to Jupyter, Notebook Classic, and now I shall open it. I go to Jupyter Programs. I have Python folders. My program is in the folder called Python, and it is here in this folder. So now it will open, and we directly will see the linear regression example solved in Python. Here it is. So this is our example. As usual, in Python, at first we import all the required libraries and functions and classes which are necessary and which we will use in the program. So here at first I have imported NumPy as NP. NP here is an alias, and imported pandas as PD, and also PD here as an alias, and also the matplotlib here. This is really, I don't remember if I plotted something or not. No, I didn't plot. It is additionally given here. It is not required because I am not going to plot anything here. I have imported from the model selection which exists in SKLEARN the model which is train test split, which is going to divide the data set to two major parts, one of them for training, the other one for testing. And after that, I have also to import from the linear model, linear regression algorithm, which is going to be used. And at last, I have imported two different metrics which are going to be used to define the accuracy of fitting or regression. Now, as a beginning, I have given a seed for the random generator with a number 42. As I told you before, this is just necessary to keep the generator giving the same values for every new run. The data set which I am going to work with is the Boston housing CSV file. So the data here is related to Boston housing. It is in a CSV format, comma separated values. And I have really downloaded it from Kaggle internet site to the documents. Now it is given a URL, and this is URL here represents that it is in the disk driver C users del documents. And it is now existing in the documents with a name called Boston Housing CSV. This URL here is assigned to a variable called data URL. And now I read this URL by using read CSV function, which is a pandas function. So from pandas PD, I call this function read CSV and pass there the URL directly, and it will give me the it will read for me the CSV file as a data frame. So now I shall have a data frame with rows, with columns, names of the rows and names of the columns. No, names of the columns only. The rows will have indexes. To be sure, I am reading the data frame head. Only 3 rows are going to be shown because I don't want to occupy a big space here. So if I read it now, I go to DF3, here it is. Now, this is 0, 1, 2, these are the 3 first rows, and this is the index of the rows, 0, 1, 2. These are the values of each of the features included in the data frame. Here, this slash means that we are continuing here in the second line. This is the first, let me say, line. This is the second line. So the number of features which we have here are 13, as I know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Number 14 column here is not a feature, it is a target. And for making linear regression, we have to separate all the data set to 2 parts. One of them which represents the features denoted by X, and the other part, which is the target, denoted by Y. The target here will be only this column. If you note what I have also done there, I have also, after reading the URL as a data frame, I have also printed the information of the data frame through the info function. This info function gives you shortened information about the data set. This is very useful because, as you see here, it shows me, for example, that I have 506 rows, the entries, all the rows or entries here, 506, beginning from 0 and ending with the 505. And the columns are 14 columns, the total, including the target one, which we have seen here. Also, it gives you the names. If you do not know the names in any way, here is the name of each of the columns. As you see, up to the number 14, this is index 13, but it is number 14, which represents the target. Okay, so we go back. Now, this DF will be divided to two parts. One part denoted by X, this is a variable called X, which include all the first 13 columns, which represent together the features of the data frame, the features of the data set X. Note here that it is a two-dimensional array. The last one, DF, I am assigning or slicing from a data frame the last column and assigned it to a variable called Y. So now I have X, the features, and Y, the target column, and now I can use them to realize the linear regression process. Or for additional work, I have printed the X shape. It will be 506, comma, will be 13, and the Y 506, comma 1, because we have only one column. If you go downwards and have a look, maybe you can see it. Yes, 506, comma 13, 506, comma. There is no one here because in Python we do not write the first one. So now we have the data set. Now it is known to us. It is ready to be used. Now we make use of the function train test split. This is the brackets of the function. We pass to this function X and Y as the data and ask the function to divide the data with a given proportion, 20% to be assigned for the testing and 80% will be assigned for training. So now we have the values of X train and Y train, which are 80% of the total value, which is 506. And we have the X test and Y test, which represent the 20% of that total also. Having these objects now, we can go further. At first, we initialize the algorithm linear regression, we call it, and assign it to a variable called model. And we use this model to fit the data set of interest, which is X train and Y train. We are we use the X train and Y train values to train the model on them, to define the most interesting features there. Now, after fitting, the model now has the necessary information about the dataset, and we can ask it to make predictions. But predictions, as usually, we do with the X test. So a model, we call the predict function and pass to this predict function the X test portion, which is here, and accordingly we get the predicted values for each value of the X test. I have printed the first 4 rows of them downwards. You can see it. Y predict 0, 1, 2, 3. This is the 4 first values because we have only one column or one column, and each of them represents a value in a row. So we have trained the algorithm, we have used it to predict different or specific values which we have selected, and now we want to measure or to know a little bit about the quality of regression. I have used firstly the mean square error and passed there the Y test and the Y predict to compare between them and to get an idea about the mean square error. Or I can use also the Y test and Y predict and pass them to the R squared score, and I get the R squared. The values here are downwards here because here it is mean squared error is comparatively a little bit high, 24, but the R squared score is 0.67. This is really acceptable. Remember, we have talked about that. As the R squared score nearer to the unity, it is better, and as the MS is smaller and approaches 0, it is better. Remember this value, please. We will compare it with the value which we will find with the PLAIY function, with the PLAIY algorithm. The intercept also is calculated. It is about 30. We shall also compare it with the value which we will get with the PLAIY function. These coefficients represents the slope for each of the features which we have. As we have 13 features, so now we have 13 values. 4 by 3, 12, and this is one, the last one is the 13, so we have 13 values. Okay, so what we have done, we have, as usually we do, we have implemented linear regression for the data set of Boston, and we have also evaluated the performance and found the attributes related to this data set. Okay, now with this we finished. Let us go to LabVIEW, to our program. So we are here. In order to work, we at first need to have the data set. The data set could be used and imported from the same PLAIY library, but I did not do that. As you see here, this is a file path. I have already downloaded the data set in Python. You remember in the previous example, which I have discussed with you, I have already downloaded the data set, and it exists with this URL here. So I can use it directly and feed it to the input of the path here of the read delimited spreadsheet VI, and I get at the output the data as a two-dimensional array. If I double click it here, here is the data of the Boston house data set, and this has a shape, as you remember, 506 columns and 506 rows and 14 columns, including the last one, which represents the target. I have compared the values. Of course, I was very interested with this to be sure that they have the same values exactly. Of course, they have exactly the same values. Here, the first row, as you see, has 0 values. So in LabVIEW, I have omitted this row, and now I have this data set with the same values except the first row. Now what I have done also, I have cancelled, or I have deleted the last column, and you kept it aside. The other 13 column data set values here represent the features. Here they are. Here is the array, which represents two-dimensional array, which represents the X features, and this is the array which represents the only one column, which is the target. I have found in LabVIEW, really, this is the target, 506 rows with one column. Here it is. And this is the size of the array, this array, which includes 506 rows also, but 13 columns. These are 13 columns. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. This is the 14th because this is before, but now here it is only 13. So now let me go back to the block diagram. So as a result of using the delete from array function here, I deleted the 0 values, and I deleted the last column, and at the end now I have got 2 arrays. One of them is the X array, which represents the features, and the other one is the Y array, which represents the columns. This is the Y array. To be sure, I have also here found their sizes, as I have shown you before. This is the size of the column, and the other one represents the size of the features. So everything is exactly as wanted. Now the X and Y are fed to a specific function in PLAIY, which is called split data set XYVI. So this is the analog to the function in LabVIEW, which we have, to the function in SKLEARN, which we have just now mentioned, which is the split, which is the test, split, and train function. This function now has the input of the features and X, and now at the output it will give you, it's split to a training portion, X and Y, which is 80%, as I told you. So I have now here the X training portion, the Y training portion, with a percentage of 80% of the whole data set. Meaning by that, 80% multiplied by 506 will give you the number of rows of X, which will be equal, of course, the same number of rows of Y. And here we will have the 20%, which is assigned for X test and Y test. So now we have the two groups, X train, Y train, X test, Y test. We have to feed that to the program. This, at first, we have initiated the algorithm by using this initiate VI, and we connected its terminal with it, the output with the value here. To feed the X train and Y train to the linear regression PLAIY regressor, we need to use a property node. Property node, as usual, exists in the block diagram only. And if you connect it to any object, it automatically adapts to that element. And by using this property node, you can assign or give the necessary or pass the necessary values to the regressor. So the X train now is passed through the initiator to the programmer, to the linear regressor, and the Y train. Now X train and Y train are existing, and the PLAIY regressor can use them to make fitting regarding this data set. X test and Y test will be used only for prediction and in order to judge about the quality and the performance of the linear regressor. So the X test is also passed, and the Y test will be also passed to another property node, and they will be also passed to the fit VI. This is the set parameters VI now already has fed the values to the regressor. So now the fitting VI or VI fit is ready to give values to the predictor. Now we take it to the input of the property node, and the output here is fed to the predictor. So at the output here, at this point, you will feed this point C. Really, this represents the values, the column values, which are predictions by the linear regressor for the X test. In order to find the quality, here we use the score VI. The output here directly gives an indicator which shows you the quality. The quality here, I will run it with you now. It is here given 0.66. Remember, in the Python, it was 0.67. And no problem, no difference at all. It gives the same values. Here I have also get at the output the printed, especially the tested values and the predicted values, to have an idea how far they are from each other. And this is, of course, manifested by the value of the score. Okay, now we go further. So we have predicted, as you see, the values. Now I used the predicted values and the test values in order to calculate on my own, on my way, the score value. I have done this before in previous lectures for you. Here it is a repetition, some kind of repetition, but in any way, I have done it twice, and here at the output I get the score which was calculated by this score VI. This value which I have received here is 100% the same. There is no difference, only at the fifth digit the difference. So now I am sure that the function, the linear algorithm, works very fine and the accuracy is very high. Also, I have made a plot to compare between the scatter plot of the data set X train, Y train, and the data set which I get as X test, Y test. I wanted to compare X test, Y test with the X test, Y predict. So I go to the front panel. Here is the scatter plot of the predicted values, and this, the white, is the test values. Of course, I can show them as points also here. Here you see how they are close to each other, but here I have done this really twice so that you can look at this graph here and see it at this graph here. But by using your eyes, you can judge that there is a high degree of accuracy, which was really shown as 67%, which means it is an acceptable value. Yes. Really, in this example, we did not use any scaling of the X train and Y train values. We did not make any feature scaling. So this error, as you see, appears clearly, but really we can improve the situation by using another adequate means to refine the data set, to minimize the difference between the values of the columns. Because if you look at the values, for example, look, in this column here, the values are 0, 0, 0, 0. Here it is 6, about 6. Here it is about 2. Here it is 29. So there are different ranges, and this really affects the accuracy which we will get. If we scale it by using one of the available methods which we have done in Python, these things, of course, are existing in PLAIY, and we can use it in PLAIY also. I remember I have looked at them. If you go to PLAIY here, data processing, you will find here something like data pre-processing, fit transform. I have to seek for, I have found it really. It takes time to find it, but they are existing. I am sure they are existing. Okay, now if we run this program to be sure that everything is okay, I go to the arrow and run it. As you see, I have to wait a little bit. Now it is already run. If I go to the front panel and look at the results that I achieve here, .674, .674, they are exactly the same. If you look at the intercept here, it is 34. And in Python, it was about 30. It's normally. This is the values of the coefficients. They should be 13 coefficient because we have 13 features: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So as you see, the play function works well. It gives practically the same results, and I advise you to work with it. In this lecture, it is just an introductory. I shall work with you on PLAIY also in the coming 2 lectures, trying to show you other or to work with other regression functions in addition to the linear regressor. With this, we finish this lecture. I hope that it was very useful to you, and it will open a way for you to work with LabVIEW freely without any Python nodes and directly by using PLAIY. As I told you at the beginning, PLAIY is not published yet. You cannot find it easily, but I have given you the GitHub repository or depository. There you will find it and you can download it. But in other places, up to now, as I know, it doesn't exist. Okay, with this, I finish this lecture and wish you the best and goodbye.